Let's now move on to our lesson on how Kc helps in predicting the extent of a reaction. The numerical value of the equilibrium constant helps us predict the extent of any reaction. It indicates to what extent a reactant converts into a product. In fact, it also measures how far a reaction proceeds before establishing the equilibrium state. Now, to understand clearly, there are three possibilities in predicting the extent of reactions. We begin with the case where numerical value of Kc is large. In the case of a large value of Kc, usually above the value of exponent 3, this tends to indicate that almost the entire mixture contains products and a negligible amount of reactants. This is because most of the reactant has turned into the product, meaning the reaction is almost complete. An example would be the oxidation of carbon monoxide to form carbon dioxide. The reaction takes place at 1000 Kelvin. In the reaction, 2 moles of carbon monoxide react with 1 mole of oxygen to form 2 moles of carbon dioxide. You can have a look at this equation here. The value of Kc is 2.2 multiplied by 10 raised to the power 22. The exponent 22 is suggesting that it's a very large value. We can assume that at equilibrium, the forward reaction is almost complete. The reaction mixture consists mostly of carbon dioxide, and the concentration of carbon monoxide and oxygen are negligible, right? Next, we'll look at when the numerical value of Kc is small. So, when the Kc value of a reaction is small, usually below exponent of -3, it indicates that the equilibrium has been established with very small conversion from reactants to products, and reactant is fairly stable. At this position, almost all reactants are present, but the amount of products is negligible. This type of reaction does not achieve completion. Let's take a look at this reaction. In this equation, 2 moles of ammonia decompose reversibly to form 1 mole of nitrogen and 3 moles of hydrogen. The value of Kc for this reaction is 3 raised to the power -9. The -9 shows us that it is a very small value. We can assume that in this mixture, it is the ammonia which is mostly present, and a negligible amount of ammonia is converted into nitrogen and hydrogen. Lastly, we'll look at whether the numerical value of Kc is neither small nor large. In these reactions, there is a comparable amount of reactants and products in the equilibrium position. It means that at equilibrium, the amount of reactants and products are relatively close to each other. For example, when dinitrogen tetraoxide decomposes to form nitrogen dioxide, the value of equilibrium is 0.211. This is neither too small nor too big. In this specific situation, we can assume that the value of Kc lies between the range of 10 raised to the power -3 and 10 raised to the power 3. This means that the rates of decomposition of dinitrogen tetraoxide and the combination of nitrogen dioxide to form dinitrogen tetraoxide are almost comparable to each other. So, I guess it is quite simple to find out the extent of a chemical reaction by looking at its equilibrium constant value. This brings us to the end of this chapter. I hope you have a clear understanding of all the concepts and problems that we have discussed.